Hi, in this video, let's take a look at this Racal-Dana 1992 frequency counter. I bought it recently on eBay for around $40 shipped, and of course, as the price might have suggested, this frequency counter has some issues and it only works partially. So to demonstrate, I'm feeding in a signal from my BK4011 function generator at around 5 MHz into channel A. And let's first verify the signal. I set my multimeter to frequency counting mode. And as you can see, the frequency here is at roughly 5 MHz. So if I put the same signal into channel A, let's just start this frequency counter. And let's turn off the multimeter here. So if I put the same signal into channel A, and as you can see that nothing happens. Right now we're setting to count frequency A, and also all the settings look correct. So even if we auto trigger DC couple, AC 50, so it doesn't really matter what I choose, and it doesn't seem to work. And now if I run some diagnostics according to the service manual, diagnostic routine 77 and 78 checks channel A and channel B, and you will see that we're getting some error codes. So let me just demonstrate that. So if I run, let me get this first into check mode. So let's go down to check, and if I remember this correctly, 77 shift store SF shift SF. Here we go. So that's the first error code, 51, and then gives 53. And then the same thing happens if I run for the other channel. So let's just get it out of here. 78, shift, store, SF, shift, SF. So again, as you can see, we have error code 56 and 58. Now, if you look at those error codes, those suggest that there's something wrong with either the amplifier or the relays of these two channels, and it didn't really give a lot of information. But nevertheless, there clearly something is wrong with these two channels. The good news is that channel C does work, so I will show you that. So here I have a signal coming from my WaveTech 395 signal generator, and that one right now is outputting 50 MHz because the channel C can only measure 40 MHz and above. So let's actually first take it out to the standard measure mode. Let's just clear this, and we'll set this to frequency C. So let's put this in, and as you can see that we are getting a 50 MHz. So this is certainly good news, and this suggests that the measurement circuitry and the microprocessors are probably working just fine. And the most likely scenario is that something went wrong with channel A and channel B subsystem. And depending on where the failure mode is, we might be able to fix it. So here I just going to show you quickly the block diagram of the system. So as you can see that we actually have a separate front end for channel C and channel A and B. So the majority of the system which taking care of the counting appear to be working fine. So our failure mode is isolated in this channel A and channel B, and possibly both the circuits. And just to give you a little bit more detail, here is a slightly detailed diagram of the channel A and channel B subsystems. And as you can see, we have some attenuation and some switching, some filtering, and possibly some digital to analog conversion happening here. So we will have to take a look in detail to see where the error might have occurred. And as many of you know, this Racal-Dana frequency counter uses quite a few custom chips inside. So if anything went wrong with those chips, you are pretty much out of luck. And as you probably know, the Racal-Dana company no longer exists as Racal-Dana. Now it's part of Astronics. So what I found out very interesting is from Astronics' website telling us the history of this whole thing. And as you can see here, that the Racal-Dana company existed from 1977 roughly to 1990, and as I highlighted here, And then afterwards it changed to many hands, finally became part of electronics. So I thought it was interesting to point out. So let's take a look at how a frequency counter works. In general, there are a couple of ways for counting frequency. The first one is probably the most popular one, and it's very intuitive, is that we have a signal here. So let's just draw it here. This is my incoming signal. And basically the idea is if I open the gate for a predefined number of seconds or predefined period, let's just say 1 second. And here is my gate. So I start counting and I stop counting. So I count how many pulses are there for this given duration. And in this case I have 2. So now the frequency would be 2 Hertz if the gate duration is 1 second. Now this is very intuitive, but it does have its drawback. And as you can see, the first thing is that depends on where the input pulse lands in terms of your gate opening and stopping. And you could count different number of pulses. So in this case, for example, if I open the gate slightly later, then what I would do is I would actually start here and end here. So now instead of 2 pulses, I would have counted 3 pulses. So this is the classic plus minus 1 count 0 error. For this error to be insignificant, we have to have the condition that the input signal is significantly faster than your gate duration. In other words, the signal here needs to be magnitudes faster than 1 Hertz. Otherwise, in this case, for example, then you get 33% of error due to this plus minus 1 count problem. But as you can see, if the input frequency is much higher, let's say 1000 Hertz, then the plus minus 1 only account for about 0.1% of the error. So clearly, this plus minus 1 error is inversely proportional to the input frequency for a given gate duration. So how do we make the measurement of a lower frequency or the frequency comparable to your gate opening duration more accurate? Well, one obvious choice is let's say if we are measuring a let's say 5 Hertz signal, I can make the gate very long. I can open the gate for, let's say, a minute, right? So then you're counting about 300 pulses. So that clearly will reduce this plus minus 1 error, the contribution to your overall frequency measurement. But that is impractical. So do we have a better method to do that? Well, that leads to our second method of counting frequency. So now let's take a look at the second method, the so-called reciprocal counting method. In this method, as the name suggests, instead of counting the number of pulses of the unknown input signal with respect to the given time interval we're using the unknown signal as our triggers for starting and stopping of the counter, and counting the number of clock pulses elapsed in between. So let me illustrate here. Again, we have our unknown signals here. And remember, in our previous standard counting method, what we're doing is we essentially set a time interval here, and we are counting how many of this unknown pulses are there within that interval. So here, we're using a slightly different method. And instead of setting the time, we're using the input pulses to set the time. So the gate opens and closes by the edges of our input signal. For example, we start our counting here, and we end our counting here. So now this is 1 period. And this time is unknown, but we do have our known clock signal. So we can count how many clock pulses here are there within this interval. And given the clock frequency and the number of clock pulses here, we can calculate the frequency of the unknown signal. Now, there are obviously quite a few advantages to this method. For example, if I wanted to make it more accurate, I can include more input pulses instead of just 1. I can count 10 pulses and use that interval to average out the uncertainties of my clock counting here. Also, when the input frequency is quite low, as you can see here, we are only taking 1 pulse, right? So when our clock signal is significantly fast, for example, a typical clock is 10 megahertz, and you have considerable number of clock pulses within this range, and that's the error due to the plus minus 1 counting. It's can be ignored. Of course, we're still having that plus and minus 1 error because the clock here is free running, and it depends on where this incoming pulse starts. You might be counting 1 less or 1 more of your clock signal. But for a given time period, so we can, for example, the input is 1 pulse or multiple pulses, but as long as the input, this time interval is fixed, our plus minus 1 error is precisely the same and can be predetermined. So the reciprocity of this method lies in the fact that instead of counting the number of pulses in the unknown signal for a given period of time, we are counting the number of clock pulses within a period of time that is determined by the incoming pulse. So those are actually the 2 main counting methods, and a lot of the modern frequency counters all typically use the reciprocal counting instead of the standard counting method. And now, of course, there are other methods. For example, if we want to totally get rid of the plus minus 1 error, how do we do that? Well, so again, we have our signal coming in, and we have our free running clock, right? So the idea is, at a certain point, we can find a trigger that the clock's rising edge matches our signal's rising edge. And so let's say we use this to start counting. Using our reciprocal counting method, we can start counting when these 2 edges align. And then we let the counter run for a while till the time comes that, let's say the start and, well, sorry about that. Let me just draw a few more. The start and the falling edge of the clock signal and the input signal matches again. So here. So this type is TC, and then we can use the number of counts we obtained within this time period to derive the input signal's frequency. Now, obviously, from this way you can see that because we're aligning up the input pulses with the clock pulses, there's no error in my clock pulse counting because the clock pulse is no longer free running. It's actually latched on to your input signal. And so in this way we can totally get rid of the plus and minus 1 frequency error. Before I open it up, let's just quickly take a look at the outside of this unit. And many people have issues with these keys, and this unit actually is pretty good. The only key that doesn't quite work is this 5, but I suspect that's because it's part of the recall, so a lot of the key is also functioning as recall parameters, so probably that was used heavily before. But that said, everything other than that key works perfectly well, and this unit is rather clean. And so I'm hoping that I can fix it. So now if I look at the side, it doesn't tell me any options. So typically this unit especially has a ovenized oscillator as one of the options. I think it's 04, something like that. But this one I don't see that. So I'm not even sure that what type of time base this has. And but all in all, it looks pretty clean, and the rear you can see this one is still has a sticker over the frequency adjustment, so probably hasn't been used for a long time or calibrated for a long time. So we will have to open it up and see exactly what is going on. And here I just open it up, and surprisingly, this one actually has a galvanized oscillator as well. So as you can see here, so this one is actually the galvanized oscillator. So now let's, I think I need to take it further apart a little bit more to reveal the actual circuit underneath, because here this top board is only for the GPIB, and which we're not interested in for this repair. We have to take it out and see what is going on underneath. And I just removed the GPIB board, and also I removed this galvanized oscillator so that we have more space here to see what is going on. And before I move forward, I'm just going to show you the GPIB board, and here is our internal of this Racal-Dana 1992. And so on the top of this, everything looks pretty clean. There's nothing that I can see obviously went wrong. So let's flip it over and take a look at the bottom side. And here's the bottom side. And the first thing I noticed is it seems that it has been reworked quite a few times. I'm not sure if you can see this clearly on the camera, but quite a few of these solder joints, like the ones here, and even here, and even here actually. So this one, they have been reworked quite a bit, and some of these even up here, I can see that these are being reworked. So let's zoom in a little bit, and you can see that. And this part is actually particularly troubling. It seems, not sure. Oh, wait a second. Did you see that? I can actually. So this resistor is actually broken in half. I can actually lift this. So clearly that's some issue with that. And we will have to take a look to see what resistor that is. And just by looking around, other than that area and a couple of areas that have been replaced, as you can see here, this one also has been replaced, or it's just not well done the first time. And similarly here. So besides these points, and this one also, as you can see here, it's a little bit of extra solder, and so potentially these things were also replaced. So okay, so I think we have enough to get started, and the very first thing I wanted to concentrate is what exactly that resistor was. So this was the one that was problematic, and we lifted it off right off the PCB when we were trying to probe it. So hopefully that can reveal some clue as to why channel A and B was not working. So the problem actually turned out to be a little more complicated than what I originally thought. If you recall that we have this resistor that was totally burned, so I replaced it, and as you can see, this one here, I don't have a 0402 resistor, which are the ones they used before, but I do have 0603s, and they fit a little bit awkwardly, but nevertheless they do fit onto the original footprint. So anyway, so that resistor here, this is for channel A, and as you can see is our resistor from your VCC to the rest of the circuit. So clearly the reason that was burned was because somewhere within this circuitry is shorted. And by the way, so I also replaced the one on channel B, the R112 10 ohm and R146. The reason I replaced those is because I was doing some measurements and these were a little bit off of the 10 ohm. So just for precautions, I actually swapped them with this known good resistors, also 0603s. So as you can see here, so this one resistor, and this is the other resistor that I replaced. So now the reason that originally this resistor was burnt obviously was something was shorted here. So I went ahead and started painstakingly measuring every single component between the positive rail and the negative rail, trying to figure out what could possibly cause this circuit to draw excessive current. And surprisingly, if I measure every single component, it looks fine. For example, with respect to ground, the resistance seems to be normal. However, if I measure directly between the positive rail and the negative rail, the resistance is very low. So that made me shift my concentration from those individual discrete components back to this IC. The reason is this is the only active component that is powered from both rail. So, and if I measure this pin 7 to pin 4, I got a very low resistance reading. But if I measure pin 7 to ground and pin 4 to ground, the resistance are okay. So that made me believe that this IC was defective. So let's take a look at the other side to see what I found. And to get to the IC, actually it's a little bit more involved. I had to actually desolder this plate from the bottom. So originally this were here. I think either, yeah, this way. Basically I have to desolder that because this was blocking some of the pins I tried to measure. And also I had to remove the, if you remember here, we had this shielding cover here. I had to also remove that. So after I took out the IC originally there, and I can confirm that it was definitely shorted. So I can show you here. So now let me first move this away, and so let's turn this on. So let's turn it into ohm range. So here is the CA3140 that I took off from the frequency counter from channel A. And if I measured pin 4 and pin 7, so these are the VCC and the VEE, the two rails. And what you get is 44 ohms roughly. And the other way around, it's also around 44 ohms. So clearly something went horribly wrong with this IC. And so I went ahead and replaced it. So as you can see here, I'm going to move this here back. And so there I replaced, this is my replacement IC, and I put it in the socket. Now I don't have a CA3140 on hand, but I have plenty of TL081s. So these two are actually pretty comparable. The bandwidth gain for the TL081s is slightly lower than the CA3140, but in terms of the other parameters, they are pretty comparable. The only difference, the major difference, is that the CA3140 has a strobe pin, which is your pin 8. And basically, the idea is you can turn the output on and off by strobing this pin. Whereas TL081, the pin number 8 is left unused. So if your circuit, utilizes that pin, then you can't really swap it. But in this case, pin 8 is not used, so I replaced that with TL081. And as I mentioned before, every time you replace an IC, it's always a good idea to include a IC socket, as I did here, because you spend so much time just trying to get to the IC, might as well just make it easier. In the future, you need to do some work on it again. So anyway, so that seemed to have fixed the frequency counter. So I will demonstrate that to you and show you, this in action, and to see that we indeed have fixed it. So while we have those open, let's just briefly take a look at how this frequency counter, the internal construction is, and we can see how exactly it works. So here are my BNCs coming in, channel A, B, and the middle one is C. And channel C is different because it counts higher frequency. So you can see this shielded box. This is for channel C. So let's first take a look at the channel A and B. Channel A and B, as you can see, they're virtually identical, and there are some relays to switch the input attenuation. And then we have these two amplifiers, basically to condition the input signal. And then we have this A to D converter, and then we run through some differential amplifiers. This board here is, I think it's NE521, I believe. Let me just take a closer look at it. Yes, so it's NE521. So that's a differential amplifier. Basically, the signals are amplified differentially for increased bandwidth. And as you can see, that this differential amplifier is actually a separate circuit board. And so they make it, I suspect, is that to make sure that this portion, the spec, is tightly controlled. And then, afterwards we go to some custom circuitry. Basically, are the controlling the gate and controlling the timing display is back here. So pretty much, everything is exactly how a frequency counter typically works, as I explained before. And so that's about it at a very high level. So let me just power it up briefly and show you that everything is indeed working. So once it's up, supposedly if I put a signal to channel A, it should show. So this is the same signal that I was using before. It was a 50 megahertz signal coming from my WaveTech 395 arbitrary waveform generator. So if I put this into channel A, and as you can see, indeed, it's working. Now the last digit is keeps increasing. That's because I just turned on this this frequency counter, and it's still warming up. So after about 10-15 minutes, it should stabilize to just around 50 megahertz. Okay, so now let's take a look at the channel B. Let me just unplug it. And the channel B, to get that to work, you can already see that as soon as I put the channel B in, the triggers are working, but it's not displaying anything yet. So what we can do is we can actually swap, at least on this particular frequency counter, we can swap the channel A and B. So we can use this channel to trigger A. So how do we do that is we, let me see if I can remember that. It's 21, shift, store, SF, and we turn on. Here you go. So now we can see that indeed both channels are working. So just to verify that our channel C is still working, let me unplug this again, and let me just briefly put this on to channel C. Don't worry about that. That's because I haven't put the shielding cover back on. As you can see, those are still here. This is for the bottom, and this plate is for the top. So I have not put those back yet. So let's change this. So there's some interference, but let me change this to channel C. Here you go. So indeed it's 50 megahertz. So now it seems like all three channels are working, and I'm quite happy about that. So now I let it run for about half an hour, and everything seemed to have stabilized. So now you're seeing is the frequency from my WaveTech 395 arbitrary waveform generator at 50 megahertz, and no problem at all. So the rest, what I need to do is just to put the shield back, and also the shielding at the bottom of the circuit board. I would need to solder that back, and then this frequency counter is totally repaired. And I hope you enjoyed the video. If you did enjoy the video, please give it a big thumbs up, and I will catch up with you next time.